Hi friends, you're watching GATE Helpline, and in this video we will see GATE 2017 CS question paper subject-wise solution for computer organization and architecture. Friends, please hit the subscribe button and click the bell icon to get all the latest updates from our channel regarding GATE exam. So friends, let's start taking questions one by one. So the question number 7 is the n-bit fixed point representation of an unsigned real number x uses f bits for the fraction part. Let I equals to n minus f. The range of decimal values for x in this representation is, and the options are A, B, C and D. So in this question we need to find the range of decimal values for x. So we can solve this by eliminating options as well. Here we know that for any decimal number fixed point, lowest bound is 0 only. Now we are left with option C and D. Option C is also wrong because the range of decimal numbers, as for n bit we can represent up to 2 raised to power n minus 1 only, but here it's given 2 raised to power n. So answer is option D, but still we need to see an example to solve this. So now we will see an example. Let n equals to 5 bits, f equals to 2 bits, that's the fraction bits, and I is equal to n minus f. So this is the representation for n bits, that's x dot xx. Here f is equal to 2 bits. So we are having the fraction bits as the 2 bits and the rest are the index bits which we got from n minus f, that's 5 minus 2 is equal to 3. So these are the 3 bits. As we know, in decimals minimum value is 0. So substituting the 0 in this format, so what we got is 000 dot 00, which equals to 0 as the minimum value, and for max value is 1. So substituting 1 into this format, we got 111.11. This is in binary, so we'll convert it in decimal, which results in 7.75. So check the max value for option C and D, because we are left with C and D only, as the rest of the options are not having minimum value as 0. So substituting this value and we get the output 7.75 from option D only. So as per our discussion, answer to this question is option D, that is 0 to 2 raised to power I minus 2 raised to power minus f. And the question number 9 is, when two 8-bit numbers A7 to A0 and B7 to B0 in 2's complement representation with A0 and B0 as the least significant bits are added using a ripple carry adder, the sum bits obtained are S7 to S0 and the carry bits are C7 to C0. An overflow is said to have occurred if, and the options are A, B, C and D. Now we will see explanation to this question, starting with method 1. Arithmetic operations have a potential to run into a condition known as overflow. Overflow occurs with respect to the size of the data type that must accommodate the result. A condition that occurs when a calculation produces a result that is greater than what a given data type can store or represent. First, when two signed 2's complement numbers are added, overflow is deducted if both operands are positive and the result is negative, which we can consider as A7 dot B7 dot S7 bar, where A7 and B7 are the operands as they are positive and the result is the sum bit S7, which is considered as negative result. Second, both operands are negative and the result is positive, which we can implement with A7 bar dot B7 bar dot S7. Or when two unsigned numbers are added, overflow occurs if there is a carry out of the leftmost bit. Now we will see method 2. Method 2 is very simple. A XOR operation can quickly determine if an overflow condition exists. That is, if we XOR A7.B7 with S7, then the resultant which we get is this, and which is equals to 1. So as per our explanation, answer to this question is option C, that is A7B7 dot S7 bar plus A7 bar dot B7 bar dot S7 is equals to 1. So friends, question number 49 is, consider a RISC machine where each instruction is exactly 4 bytes long. Conditional and unconditional branch instructions use PC relative addressing mode with offset specified in bytes to get target location in the branch instruction. Further, the offset is always with respect to the address of the next instruction in the program sequence. Consider the following instruction sequence. This is the instruction number and instructions which the instruction sequence table is having. If the target of the branch instruction is I, then the decimal value of the offset is dash. So now we will see explanation to this question. In question we are given with each instruction is exactly 4 bytes long. So now we are having a table which is having instruction number and bytes which each instruction will occupy. So as we are given that exactly 4 bytes long each instruction will be, so for first instruction I, it will be from 0 to 3, and for I plus 1 it will be 4 to 7, and similarly for the instruction I plus 3 it will be 12 to 15. So the next instruction will be having address 16. So according to PC relative mode, the effective PC address equals to next instruction address plus offset. So here we need to calculate this, the value of offset. So we start with 0 equals to 16 plus offset, as the next instruction address is 16 and we need to find the offset. So by doing the mathematical calculation, we send this 16 to the LHS and the value of offset will be negative 16. So friends, as we have discussed earlier, the answer to this question is minus 16 is the decimal value of the offset. So question number 50 is, instructions execution in a processor is divided into 5 stages. Instruction fetch IF, instruction decode ID, operand fetch OF, execution EX and write back WB. These stages take 5, 4, 20, 10 and 3 nanoseconds respectively. A pipeline implementation of the processor requires buffering between each pair of consecutive stages with a delay of 2 nanoseconds. 2 pipeline implementations of the processor are contemplated. First, a naive pipeline implementation NP with 5 stages and an efficient pipeline EP where the OF stage ID divided into stages OF1 and OF2 with execution times of 12 nanoseconds and 8 nanoseconds respectively. The speed up correct to 2 decimal places achieved by EP over NP in executing 20 independent instructions with no hazards is dash. So now we will see explanation to this question. In question we are given with total number of instructions n as 20. So first of all we will start with the naive pipeline. Here the number of stages k is given as 5 and the clock time TP we calculate with the help of maximum of stage delay plus buffer delay. So here the stage delay is the time taken by the processor at each stage and the stage times are given in the question. So we have added the buffer delay in the stage delay. The buffer delay is constant, that is 2 nanoseconds for all. So after adding stage delay and buffer delay we get 7, 6, 22, 12 and 5, and the maximum of these is 22 nanoseconds. This stage delay. Execution time ENP equals to k plus n minus 1 into TP. So here we know that k is 5 from here, n is 20 the number of instructions and TP is clock time. So we can calculate easily, that is 5 plus 20 minus 1 into 22, that is 528 nanoseconds. The second part of this question is for efficient pipeline. So here the number of stages k is 6. Delay with 20 nanosecond stage is divided into 12 nanoseconds and 8 nanoseconds. which is given in the second point in the question. So clock time TP equals to max stage delay plus buffer delay. So here what happens is this particular stage of 20 nanoseconds is divided into 12 nanoseconds and 8 nanoseconds. So we take it as separately and add the buffer delay. So here a 2 nanosecond buffer delay will be added. So it will be like 7, 6, 14, 10, 14 and 5. So out of these delay, the maximum is 14 nanoseconds. So now we calculate the execution time, that is E of EP, which equals to K plus N minus 1 into TP. Here K is 6 and N minus 1 is 20 minus 1 into TP, which is clock time. So it's 6 plus 20 minus 1 into 14, that is 350 nanoseconds. So in question we are asked for the speed up. So we calculate the speed up as E of NP upon E of EP, which equals to 528 upon 350, which equals to 1.508. So friends, here our answer to this question is 1.508 is the speed up achieved by EP over NP in executing 20 independent instructions with no hazard, and the given range in the GATE 2017 question paper is 1.49 to 1.52, and our answer lies between this range. So question number 52 is, consider the expression let X be the minimum number of registers required by an optimal code generation without any register spill. Algorithm for a load store architecture in which first only loads and store instructions can have memory operands, and second arithmetic instructions can have only registers or immediate operands. The value of X is dash. So now we will see the explanation to this question. In question we are given with this expression, that is a minus 1 into b plus c upon 3 plus d. So we need to do the assembly code using the load and store architecture can be written as follows. So this one is the instruction set, as we are following here two addressing mode. So here we start with this particular expression, that is b plus c. So for taking this b plus c, first of all we load b into R1 and then we load c into R2. So we had taken two registers R1 and R2 and loaded b and c. So what we need is, we need to calculate the addition of b plus c. So here we have done the addition of R1 comma R2 and the result is stored in R1. So R1 is having the result of b plus c. So in the next instruction we had divided R1 comma 3. That means this particular divide by 3 we had done, because R1 is already having b plus c. So we had divided 3 by R1. So now this R1 is having value b plus c upon 3. Now R2 is free. So we had loaded the value of d in R2. So now this R2 is having value d. Now what we need to calculate is addition of this particular expression and d. This entire expression is contained in R1 and this d we had loaded in R2. So we perform an addition operation with R1 comma R2 and the entire expression is now loaded in R1. So R1 is having b plus c upon 3 plus d. We need to calculate this expression, that is a minus 1. So R2 is free. So in R2 we had loaded the value of a. Now a is in R2. So we had performed a subtraction operation on R2 with value 1. So R2 is now containing a minus 1, that is this particular expression. This expression is in R2 and this entire expression is in R1. So now we have done a multiplication operation on R2 comma R1, so that we can get this entire expression. So here as we can see, that the entire expression we can evaluate with the help of two registers, that is R1 and R2. Hence, the minimum registers required are 2. So as per our discussion, answer to this question is the value of X is 2. That is, the minimum number of registers required by an optimal code generation algorithm for a load store architecture is 2 registers. So question number 54 is a cache memory unit with capacity of n words and block size of BB words is to be designed. If it is designed as a direct mapped cache, the length of the tag field is 10 bits. If the cache unit is now designed as a 16-way set associative cache, the length of the tag field is dash bits. So now we will see explanation to this question. But before proceeding to the question, first of all, we will see an example to direct mapped cache. So for this, assume you have 32-bit addresses can address 4 GB, 64-byte line size which give us an offset of 6 bits and 32 KB of cache size. And the number of lines we can calculate as the cache size upon line size, that is 32 KB upon 64 bytes, which result in 512. So the bits to specify which line is log base 2 number of lines, that is 512, which results in 9. So we can have this representation for the direct map where we have the offset of 6 bits. Offset we get from the line size and line number we get from cache size upon line size, that is 512. So 512 we can represent as 2 raised to power 9, which is these 9 bits. And as the total size of the address is 32 bit, we subtract 32 minus this 9 plus 6, that is 15. So 32 minus 15 is 17. So we are left with 17 bits. And we can say that these 17 bits are the tag bits. Similarly, the same example we can do with set associative cache. So these are the things we have assumed. The only difference here is the 4-way set associative. We have taken here 4-way set associative cache. So the difference which came is the number of sets. So here these lines, these line numbers are divided by the 4-way, that is this 4, which results in 128 sets, and the set bits will be log base 2 128, that is 7. So the representation of this is like this. So here we have offset of 6 bits that we get from the line size, and this set bits we get from number of sets, that is 7 bits, and the rest of 32 minus 7 plus 6 is 19. So 19 are the tag bits. So if we compare this from the direct mapped cache, we can see that here in that we have 9 bits. So those 2 bits are moved from here to here. So the difference of 2 bits are coming. So that 2 bits is we have taken from this 4-way, that is 2 raised to power 2. So similarly we can do in our this question also. So friends, now in this question we are given with an direct mapped cache. So here in question we know that the tag bit is of 10 bit and the type of mapping is direct map. For this direct map 10 bits are required in its tag. So now for set associative we want this set number. So we don't know what is the set number and what are the offset bits, but what we know is the set associative, that is k set associative. So it is updated to 16-way set associative. So this is given in question. So the new tag field is 10 plus log base 2 16, that is 14 bits. We have this 16 here because this one is 16-way set associative, and in our earlier question it was 4-way set associative. So we had taken log base 2 16 here. So because of the k-way set associative map design, log base 2k bits are additionally required to the number of bits in tag field for direct map design. So with the help of these two fields, that is the tag bit of direct mapped and the value of k from the set associative map, we can calculate the tag bit of set associative cache. So as per our explanation, answer to this question is 14 bits, that is length of the tag field is 14 bits in 16-way set associative cache. So friends, thanks for watching our video. Please like, subscribe our channel and share our videos to appreciate our work. If you have any doubt or question, please comment below and keep watching our channel for videos like this.